We are Team 26018, the Automated Dispense Volume Calibrator, which we call the ADVC. Our sponsors are Roche Tissue Diagnostics, and our team members include 3 biomedical engineers, me, Tatum, team lead, Ian Gold, Adiba, our software engineer is Leo, our systems engineer, also our procurement lead, is Michael, and our mechanical engineer, Colton. Roche Tissue Diagnostics, located here in Tucson, focuses on research and development. This includes the HE600, an automated system for individual hematoxylin and eosin slide staining, the target system to our senior design project. Our sponsors tasked us with creating a solution that will streamline the production process for the HE600. We are responsible for delivering a product that will help them automate the calibration process for the tissue staining modules that are installed within the HE600. Current calibration methods can take up to 2 days and require multiple technicians on the job. This is where the ADVC comes in. Here are the different categories for the requirements of the ADVC. We broke these down into performance, environmental, safety, interfaces, and design features. The most significant pieces here for our team while creating our design are to first ensure that we are measuring to a 2.5% accuracy of the nominal volume of our fluid. Next, to ensure we do not directly change the HE600, and to ensure that our design can withstand the dispense fluids and temperatures up to 50 degrees Celsius within the HE600.
So going into this project, we had multiple ideas for how to approach this. The first one was the load cell, as there is readily available information online and it was easy for us to utilize and also obtain load cells. There was also an idea for a camera system to track the level of the fluid, and we also had an idea for a tube-based level sensor for the fluid. And then eventually we were able to determine that we could use a capacitor, and this was supported by mathematical models and calibration curves. So the load cell immediately faced pretty significant issues during our actual implementation of it. One of the most notable things was that it was too large, and it was very difficult to actually integrate into the pre-existing tray. So the movement with the nozzle was already restricted with that matter, and that would fail one of our requirements. The actual test that we conducted was also extremely noisy, and it was very unstable anytime we measured anything. And then on top of that, the load cells were very fragile, and they would break often within the first 3 uses, and we had to get new ones.
Now, the new method our team decided to go with was using capacitance to measure the fluid level that's dispensed within the HE600. The idea came from how cars use capacitance to measure fuel levels in their gas tanks. Why couldn't we use capacitance to measure the fluid level? The initial tests were completed by using 2 parallel plate capacitors with a bunch of known dimensions and comparing it to a derivation that was completed that's also listed here on this slide, comparing the total capacitance reading and breaking it apart into an air capacitance and the fluid capacitance. From there, we were able to calculate the height of the fluid and then the volume. This eventually developed into a constant capacitance reading compared to a calibration curve, which is much more accurate. Now, the capacitance measurement vessel has changed quite a bit over the last 6 months. It began in November of 2025 with just a kind of proof of concept to see if the capacitance level sensing would even work in the first place and we'd get a positive reading. Then it quickly developed into a rushed prototype of the weighboat in December, and it still had the parallel plates in contact with the water, which we had to adapt and change. In January 2026, we changed it to the internal plates, and then we improved upon that design to the current design we're rocking, which fits flawlessly in the tray and has the embedded capacitors built in. Now here is a model of the measurement vessel assembly with the PCB capacitor plates built into it. It shows how they slide into their embedded slots. Now here is a model of our electronic housing that supports 3 different PCBs. It has ridges on the sides, so it fits in the tray around each of the weighboats, and it has holes on top for all the wires. Now here is the electronic housing for the PCB that supports Bluetooth. It has similar qualities to the previous one, except it's much smaller and it only houses the one PCB.
The measurement controller PCB has an ESP32C3 with flash and reset functionality on board and a USB-C to UART with the debugger shared through the USB-C port. It has 8 separate and distinct I2C buses with a multiplexer allowing 8 devices with the same address, and it's multifunctional so it can be used for acquisition or Bluetooth communication. The measurement sensor board has an I2C connection to go back to the primary measurement controller board. It has an 807746 capacitance to digital converter and guard rings around the capacitance measurement lines with via fencing. This consists with coaxial connections for the capacitor plate PCBs. The capacitor plate PCB has an exposed copper face with a backplane driven to the excitation voltage of the capacitor, and it features a coaxial connection to go back to the measurement sensor PCB.
This is how the ADVC hardware integrates with software. Begin by logging into the GUI, pairing Bluetooth, then loading an existing calibration curve or capturing a new one that corresponds to the current fluid. Now, the ADVC is ready to measure. As you can see, the values are now stabilizing. After about 30 seconds, the value should stabilize around the measured value, which in this case is 100 microliters. Now that the values have stabilized, the readings are consistent and noise-free with an accuracy in the range of tens of microliters. From this point, the values could be written back to the HE600 and saved in firmware to calibrate the valve timings. The ADVC extends modern DevOps principles to embedded systems, treating PCB hardware design, firmware, and application software as a unified, continuously validated system, reducing integration drift and enabling reproducible system builds across hardware and software domains. CI/CD provides end-to-end automation across the full stack, from hardware manufacturing to software development.
The team and sponsors underestimated the difficulty of this project going in, assuming that it would be a normal engineering design problem. However, we quickly realized that because of the HE600 staining module's low clearance being below 9mm, we would have to come up with a novel solution. This led us to the horizontal capacitive plates, allowing us to reach the precise, accurate requirements that our sponsors asked of us.
The ADVC poster describes our design goals to measure small volumes of fluid within an accuracy of 2.5% across 4 positions while withstanding a temperature of 50 C. As can be seen by the results, most of the measured values are within the 2.5% accuracy margin. Our tray setup can also be seen, which shows the 4 positions and 4 reference vessels, as well as the housing maintaining a vertical clearance of less than 10 millimeters.